So, welcome to the second video dealing with gas laws. But first, we'll go over the homework. So to go quickly over the homework, fluorine's electronegativity is 4, chlorine's electronegativity is 3, bromine 2.8, iodine 2.5. So in the first example, HF is going to be fluorine's more electronegative, so HF is going to be more polar. In the second one, chlorine is more electronegative, and so HCl is going to be more polar. In the third one also, the chlorine's more electronegative, so HCl is going to be more polar. And finally, HBr is going to be more polar. In problem 2, carbon is less electronegative than fluorine, so the dipole points to fluorine. Silicon is less electronegative than carbon, so the dipole points to carbon. Carbon is less electronegative than oxygen, so the dipole points to oxygen. And bromine is less electronegative than carbon, so the dipole points toward carbon. Problem 37 is straightforward, and it's based on what we already talked about, the periodic table. Aluminum starts with 3 electrons, sulfur starts with 6, so aluminum loses 3 to become a +3 cation, sulfur gains 2 to become a -2 anion. You have to gain and lose the same number of electrons. 3 and 2 is 6, times 2 is 6. So we need 2 aluminums and 3 sulfurs to make the compound. Radium starts with 2 electrons, oxygen with 6. Radium loses 2, oxygen gains 2, and it's a 1-to-1 compound. Calcium starts with 2, fluorine starts with 7. The calcium loses 2, the fluorine gains 1, so we have to have 2 fluorines for each calcium. Cesium starts with 1, nitrogen starts with 5. The cesium loses 1, the nitrogen gains 3, so we're going to need 3 cesiums to form the compound. And finally, rubidium starts with 1, phosphorus starts with 5. Again, we're going to need 3 rubidiums for each phosphorus to form the compound. Problem 59 is a has-needs problem. Nitrogen starts with 5, the bromines start with 7. They all want to get 8 electrons. 32 minus 26 is 3 bonds. That holds it together. Each of the bromines ends up with 3 lone pairs. The nitrogen ends up with 1 lone pair for itself. The 3 bromines are 18 electrons. The 6 bonding ones make it 24, and the lone pair on the nitrogen is the 26 electrons. Hydrogen puts in 1, fluorine puts in 1. The fluorine still has 3 lone pairs to itself. The carbon starts with 4. The bromines start with 7. Carbon puts in 1, bromine puts in 1. So each of the bromines has 3 lone pairs to itself and a bonding pair. The carbon has 4 bonding pairs. So the 4 bromines have 24 to themselves, and they share 8 with the carbon is the 32. And finally, the 2 carbons each bring 4, the 2 hydrogens each bring 1. That's 10 electrons. We need 20. 20 minus 10 divided by 2 is 5 bonds. The hydrogens can only form 1 bond, so we're going to have 3 bonds between the 2 carbons. Each of the carbons also has 1 bond to one of the hydrogens, and that's the 10 electrons for acetylene. That compound's acetylene. Which brings us to problem 67. Several people solve this problem using an expanded octet, which was okay. And technically the expanded octet is more correct than the regular Lewis dot structure. But the inherent requirement for using any Lewis dot structure is you do in fact have to use it correctly. Expanded octets are a more advanced concept, which is why the book doesn't mention them and I haven't gone over them. But like I said, they are technically the more correct answer. The problem is the first rule of doing Lewis dot structures is you have to show the right number of electrons. Any structure that doesn't have the right number of electrons in it is simply going to be wrong. The first one in the homework, the chloride ion, has 6 electrons from each of the oxygens, 7 from the chlorine, and one more because it's an anion. That's a total of 20 electrons. A whole lot of people solved that structure but only showed 18 electrons, which meant the structure was automatically wrong because it had the wrong number of electrons. Other than that, people either didn't bother finishing putting in all the electrons around all the atoms. It says the complete Lewis dot structure. And second, they didn't bother to put brackets and indicate the charge on the ions. Anytime you have an ion in a Lewis dot structure, you have to put a bracket around it and indicate what the charge on the ion is. If you're not doing that, then the structure isn't correct. Problem 67 has needs for ions. The chlorine ends up in the middle. The oxygens don't want to be together. They want to pick on something less electronegative. Chlorine's less electronegative, so it gets stuck in the middle. We need 2 bonds. That holds it together. Each of the oxygens ends up with 3 lone pairs. That means the chlorine with 2 bonds has 2 lone pairs to itself. So there's 6 around each oxygen is 12. They're sharing 4 is 16, and the chlorine's got 4 to itself is the 20. And we got to put a bracket around it and indicate it's an anion. Perbromate ion. Bromine's in the middle, surrounded by the oxygens. Again, the oxygens don't want to be bonded to each other if there's somebody else to pick on. Each of the oxygens ends up with 3 lone pairs and a bonding pair to the bromine. The bromine ends up with 4 bonds. And again, we have to put a bracket around it and a minus sign. It's an anion. Which finally brings us to C, cyanide. Carbon brings 4, nitrogen brings 5, would be 9. It's an anion. That's 1 more, that's 10. 16 minus 10 divided by 2 is 3 bonds, so we're going to have a triple bond between the carbon and the nitrogen. With a triple bond, the nitrogen needs a lone pair. With a triple bond, the carbon needs a lone pair. And again, since it's an anion, we have to put a bracket around it and show the minus sign. Problem 83 is, again, a has needs for ions problem. Sulfur ends up in the middle, surrounded by the oxygens. Each of the oxygens ends up with 3 lone pairs and a bonding pair to the sulfur. With 4 bonds, the sulfur has its 8. The whole thing's a minus 2 ion. Since there are 4 pairs of electrons around the sulfur, they go into a tetrahedron. And since they're all bonding, that's the shape of the molecule of the ion we get. For B, it's the same thing, only the phosphorus is in the middle. Each of the oxygens ends up with 3 lone pairs and a bonding pair to the phosphorus. The whole thing's a minus 3 ion, so we have to put a bracket around it. Again, 4 pairs of electrons around the phosphorus go in a tetrahedron. And since they're all bonding, again, we get a tetrahedral shape. And finally, for ammonium, the nitrogen is in the middle, surrounded by hydrogens. The nitrogens bring 5. The hydrogens that each bring 1 would be 9, but it's a cation, so it has 1 less electron. 16 minus 8 divided by 2 is 4 bonds. 4 bonds hold it together. Each of the hydrogens with 1 bond is fine. 4 bonds form the 8 for the nitrogen. And again, 4 pairs of electrons do a tetrahedron. And again, since they're all bonding, we see a tetrahedral shape. So, on to chapter 13. We were saying, you have a balloon and it's full of gas. Well, what do you mean that it's full of gas? The balloon's obviously expanded, and so there is gas in it pushing out against the surface, but how much of the volume of the gas is actually being occupied by the gas itself? That is, the actual molecules and atoms that are making up the gas. Let's consider a nice simple reaction. For example, sulfuric acid with sodium hydrogen carbonate. When you combine sulfuric acid with sodium hydrogen carbonate, you get sodium hydrogen sulfate, you produce water and carbon dioxide. The important thing is the carbon dioxide comes off as a gas. What we have here is a test tube with 25 milliliters of 2 molar sulfuric acid, a small test tube which includes 1 cubic centimeter of sodium hydrogen carbonate, and an empty balloon. The balloon has no air in it. What we're going to do is we're going to take the sodium hydrogen carbonate and put it into the balloon, and then attach it to the test tube with the sulfuric acid in it. So we've taken the sodium hydrogen carbonate and put it in the balloon, which still has almost no air in it, and attached it to the test tube with the 2 molar sulfuric acid. We're now going to mix the sodium hydrogen carbonate with the sulfuric acid. As you can see, the level of the sulfuric acid is the same, so it hasn't gone anywhere, but you'll notice that the balloon has in fact become inflated. It's now approximately 4 inches in diameter. So what is the volume of a sphere that is 10 centimeters in diameter? It's a fairly simple calculation. The volume of a sphere is 4/3 pi r cubed. And since the sphere is about 10 centimeters in diameter, its radius is 5. So 4/3 pi times 5 cubed is 523 cubic centimeters. So the volume of the balloon is 523 cubic centimeters. And so how much of that is occupied by the gas? Well, where did the gas come from? The gas came from our 1 cubic centimeter sodium hydrogen carbonate. The carbon dioxide was part of the sodium hydrogen carbonate. But let's be generous. Let's assume that it was all of the sodium hydrogen carbonate. So it had a volume of 1 cubic centimeter. It's now occupying 523 cubic centimeters of volume. So how much of that space, the 523, is actually occupied? Well, the atoms and molecules occupied 1 cubic centimeter. So 1 cubic centimeter divided by 523 cubic centimeters times 100%, and less than 0.2% of that volume of the gas is actually occupied by the gas itself, that is, the atoms and molecules themselves. Overwhelmingly, 99% of that volume is simply empty space. There isn't anything there. So when we said the particles in a gas are far apart, we meant they were far apart. Less than 0.2% of the volume of the gas is actually occupied by the gas. So if the gas isn't actually filling the balloon, how is it occupying all that space? What are the particles of the gas actually doing that the material ends up expanding the balloon and filling up that much space? And that's what we'll look at in the next lecture.